So then I'll introduce you, Detlef, and we'll get started. So welcome everybody again to the second to last installment of our environmental engineering graduate seminar series at Michigan Tech. Appreciate you being here today. Just a couple of housekeeping announcements. Again, if you wish to get documentation for your continuing education credits, please contact Dr. Eric Seagren, and he will take care of that for you. Another reminder, for those of you who are joining us for the first time, you will be on mute and unable to share your video, but we do welcome questions for the speaker, and you have two options for asking questions. You can either type your questions into the chat, and we'll kind of keep track of that. I can monitor that and share the questions with our speaker at the end of his presentation, or you can simply raise your hand when he's finished speaking, and we'll take you off mute at that time. So I'd like to go ahead and introduce our speaker. I'm thrilled to have Professor Detlef Knappe speak to us today. He is the S. James Ellen Distinguished Professor of Civil Construction and Environmental Engineering at North Carolina State University, and he received all of his degrees, the BS, MS, and PhD from the Department of Civil and Environmental Engineering at the University of Illinois at Urbana, and that is where I met Professor Knappe some years ago. And he joined the North Carolina State faculty in 1996, along with several of our other peers at University of Illinois at the time. Professor Knappe is the Deputy Director of North Carolina State Superfund Center, which is named the Environmental and Health Effects of PFAS, and is a member of the Center for Human Health and the Environment. Professor Knappe is interested in drinking water quality and treatment, water reuse, organic micropollutants, and related topics. He is a trustee of the American Water Works Association's Water Science and Research Division, and he is a member of the North Carolina Secretary's Science Advisory Board. He serves as the associate editor for the American Water Works Association's journal Water Science, and he also serves on the American Water Works Association's Organic Contaminants Research Committee and the Standards Committee for Activated Carbon. Professor Knappe and his students have been the recipients of numerous Best Paper, Best Poster, and Best Thesis awards. He is also the recipient of North Carolina State University's Outstanding Teacher Award and the Bill Horn Kimley Horn Faculty Award for Excellence in Graduate and Undergraduate Teaching and other accomplishments at North Carolina State University. Professor Knappe also is the recipient of the Young Civil Engineer Achievement Award from the University of Illinois. And with that, I will turn it over to Professor Knappe. And again, welcome, Detlef.
Great. Thanks so much, Jennifer, for this introduction. Yeah. The Young Civil Engineer Award, that was a few years ago, so maybe I'll get the old one soon. It's a real pleasure to join you remotely here. I'm in my daughter's bedroom. She's now in college, so you see some unusual office decorations, if you will. So let's talk PFAS today, and specifically I want to talk about the occurrence and community impacts of PFAS in North Carolina. And of course, this work wouldn't be possible with members of my group, and you see some of them here, including a picture that was taken a couple springs ago, but this is about how it looks like in North Carolina right now. And here we're sampling along the Cape Fear River, and that river will be mentioned a few times during the seminar. All right, so let's start with some definitions, because I don't know where everybody is in terms of PFAS. That's a class of thousands of compounds, and so it can be quite overwhelming to get started with this kind of research. So the class that is most well known are the perfluoroalkyl acids, and I'm showing the two most important subgroups of those PFAAs here. These are the perfluorocarboxylic acids on the on the left and the perfluorosulfonic acids on the right. So the only difference is the head group, which is a carboxylic acid here and a sulfonic acid here. And if we want to talk about poster children of PFAS, PFOA here on the bottom left and PFOS on the bottom right are probably the two most well-known. If you've watched the movie Dark Waters, that's all about PFOA, for example. People also talk about long and short chain PFAS, and this kind of definition is reasonable for perfluoroalkyl acids, but I'll show in a second that long and short chain terminology is not all that useful for newer chemistries. So long chain PFASs for carboxylic acids have 7 or more carbon atoms, whereas for the sulfonic acids is 6 or more carbon atoms. So both PFOA and PFOS are considered long chain PFASs. So apart from perfluoroalkyl substances, we also see polyfluoroalkyl substances, and the main difference there is that in the perfluoroalkyl substances, there are no carbon-hydrogen bonds, like in the PFOS case, whereas for the 6,2 fluorotelmer sulfonic acid shown here, you see there's a couple CH2 groups. So that's one way, fluorochemical manufacturers play with the chemistry, so this, for example, might be considered shorter chain than PFOS, but in many ways, from a hydrophobicity perspective, this compound on the bottom is not all that different from the one on the top. So PFASs are released into the environment through multiple pathways, but one important one is fluorochemical manufacturing. So these are sites where fluoropolymers are made, or building blocks for the fluoropolymers are made. But then PFASs are also released during the production of a lot of consumer products and the use and disposal of these products. And so you can find PFASs quite common in everyday life. So for example, the sort of poster child here is the nonstick pan. So that's coated with a fluoropolymer to make it nonstick. A lot of food contact materials are PFAS coated. So for example, muffin cups or hamburger wrappers, or whatever food contact paper you find in fast food places has often a PFAS coating. Also, our water repellent fabrics like Gore-Tex have fluoropolymers in them. And then, if you get a stain treatment for your car or your carpet, then those materials are usually PFASs as well. So like Rain-X on the car is water repellent for the windshield. Those types of products can contain PFAS as well. And then a very important introduction route for PFASs into the environment has been firefighting training areas, because aqueous film forming foams have PFASs as active ingredients. So there's a nice website called sixclasses.org that talks about the occurrence of PFASs in consumer products, and also strategies for avoiding them. And that's a really important message overall. If we're concerned about PFAS introduction into the environment, then as consumers, we also need to understand what products contain PFASs, and how we might either avoid purchasing them, or also let retailers and manufacturers know that we don't want PFASs in our products. So this kind of pressure is working. So for example, McDonald's earlier this year phased out PFAS containing food contact materials. Large chains like IKEA have been working very hard to eliminate PFASs from their entire supply chain. And carpet manufacturers are now moving away from using PFAS treatments as stain repellents for carpets. So PFASs are useful. Often, they provide convenience for us, but they are forever chemicals, meaning they are very persistent in the environment as a result of a very strong carbon-fluorine bond. They're also very persistent in most engineered water treatment systems. So typical oxidation and advanced oxidation processes do not destroy perfluoroalkyl acids, for example. They have surfactant behavior, and so at high concentrations, they can also form micelles. And some PFASs accumulate readily in people and the aquatic organisms and just wildlife in general. Also, other PFASs can be highly mobile, so they are globally distributed, and we find PFAS in polar bear livers, for example, at high levels. PFAS are therefore ubiquitous, and they're found in people essentially globally, and they're associated with adverse health effects. There are thousands of PFASs out there, like I mentioned. They're grouped in many subclasses, so people have started building these family trees for PFAS. And this is a figure from a nice paper called PFAS, The Never-Ending Story. And what's interesting here is you can see, for example, the number of citations for different PFASs. And so there are the well-studied types, and then there are others that aren't really all that well understood. So that makes PFAS research quite challenging because in theory we may encounter hundreds or thousands of PFAS in environmental samples or in biological samples. So exposure routes, it all starts with the production of the PFASs in the first place, and then through consumer products, we may get directly exposed to PFASs or otherwise through either discharges from the manufacturers or the uses of products. These PFAS enter the environment, and then we're exposed to them primarily through drinking water, but also food and inhalation. So like I mentioned, a lot of PFASs, some of these that are more well understood, are widely detected in people globally. PFOS and PFOA are likely carcinogenic and immunotoxic to people. And so immunotoxicity implies, for example, also potential that vaccinations are less effective as intended or as would be expected in people who are not exposed or exposed to very low levels. But the health effects of many PFASs are poorly understood, and the importance of mixtures here is also an important thing to consider. And we have a very little understanding of the mixture effects among the different PFASs. Because PFASs bioaccumulate in people, especially the longer chain PFASs, they're of concern at very low concentrations. So if you look at drinking water standards, most of the regulations really are for synthetic organic contaminants in the microgram per liter range, but here we're interested in levels at the nanogram per liter range. And For PFOS and PFOA, EPA has a non-enforceable health advisory level of 70 nanograms per liter for the sum concentration. But then individual states, including Michigan, have developed enforceable drinking water standards, and often these are substantially below the levels of the EPA health advisory. So since you're all in Michigan, let's maybe look at these numbers in particular. PFOA at 8 nanograms per liter, PFNA at 6. These are among the strictest in the country. And so that also means quite a few drinking water sources are impacted, and drinking water providers have to install treatment or have to figure out ways to eliminate PFASs from their source water to bring these levels down to these standards. Vermont also has a very strict standard with a sum of 5 at 20 nanograms per liter. And then GenX was first, a limit was first established in the US and North Carolina at 140 nanograms per liter, and the Michigan MCL is 370. It's interesting to look at this PFHXA level of 400,000 nanograms per liter. There's quite a bit of debate about the appropriateness of that level. And that is in part a reflection of just a lack of good toxicity data for this compound. So PFAS occur widely in drinking water, and so the Environmental Working Group has built a map of the whole country, and each of the sort of bluish green turquoise dots is drinking water. And that's impacted by PFASs, and you can see that there are clusters. These clusters are not necessarily an indication of those are hotspots, but they're also an indication of where a lot of testing has been done. And so, North Carolina, as I'll get into it, the Environmental Working Group basically looked at all of the data that's been collected as part of our PFAS testing network and put it on their map. And the state of Michigan has also done an excellent job in terms of surveying drinking water and groundwater around the state. And so have a few other states like New Hampshire and California. So again, I put this slide in because you're all in Michigan. So up here in Houghton County, everything's looking good. But Michigan is a state that has quite a few impacted sites. And so in total, there's 154 known sites that exceed the groundwater cleanup criteria in the state of Michigan. And these dots are well distributed across the state. So in North Carolina, several communities are impacted by less well understood PFASs. These are called fluoroethers, and I'll describe that in a little bit more detail. And so I'm going to focus a lot on this purple region here, the Cape Fear River Basin. It's an important drinking water source for the state of North Carolina, and about 1.5 million people depend on the Cape Fear River for their source of drinking water. And in the central part of the watershed is a fluorochemical manufacturing plant, and they discharged wastewater into the Cape Fear River and discharge PFASs into the air. And as a result, private wells that are surrounding this manufacturing site are contaminated. And then drinking water in the lower Cape Fear region, Wilmington and Brunswick County they're withdrawing their drinking water from the Cape Fear River, and they've been impacted heavily, as I will show soon. So a little bit of history here at this fluorochemical manufacturing site. Production began in 1980. This was back then a DuPont plant called the Fayetteville Works. And in 2002, when the 3M companies stopped making PFOA, DuPont started making PFOA at the Fayetteville work site. And within a very short time after PFOA production started, the groundwater beneath the plant was already contaminated with PFOA, but the public didn't find out about this for another couple of years. And as a result of the PFOA production, researchers at the US EPA here in Research Triangle Park became interested in the possibility of PFOA releases into the Cape Fear River from this Fayetteville work site. And so they published a paper in 2007 to look at PFAS occurrence in the Cape Fear River watershed. So number 5 here, this site is where the fluorochemical manufacturer is located. And if you look at the dominant PFAS at the time, it was PFOA or C8 at all sites except site 5 and 11. So PFASs and PFOA occurred upstream of this fluorochemical plant at high levels, and that was an unexpected result. And then if you look at the waste discharge channel that was transporting wastewater from the fluorochemical manufacturer to the river, PFOA was actually not the dominant chemical. In fact, it was PFHPA or C7 that was the dominant PFAS. And when you look at the tributary upstream here, the Little River, the dominant PFAS in that was PFOS. And this river, the Little River, drains Fort Bragg, a military site, and it's expected that firefighting training activities contributed to the elevated levels of PFOS at that location. So this here highlights that there are many PFAS sources in this watershed, not just the fluorochemical manufacturer. And I would be amiss at not mentioning Andy Lindstrom and Mark Streiner here. They really are true leaders in the field of PFAS research. They are at US EPA here in Research Triangle Park. And I always like to say everything I know about PFAS I learned from Mark and Andy. So continuing with the history then, in 2009, DuPont had applied for a replacement for PFOA that they called GenX. And so the idea was to replace PFOA with a shorter chain PFAS that they named GenX. And the idea was to phase out the production then of the longer chain PFOA because of the health concerns that are associated with that compound. Also in 2009, EPA began to issue its first provisional health advisory level for PFOA and PFOS at 400 and 200 nanograms per liter. And this was meant to be protective against short-term exposure. So moving on, then in 2012, we first detected GenX and other fluoroethers in Cape Fear River water. In 2014, the first time in the actual drinking water in Wilmington, North Carolina. And in 2015, Mark then published a key paper that introduced the structures for the fluoroethers that were being discharged by this fluorochemical manufacturer. And so this is a tough read, this paper, but basically describes how through high resolution mass spectrometry, these structures were identified. And you can see here that all of these compounds contain one or more ether oxygen atoms. And there are homologous series here. So we have a monoether series where the CF2 number of CF2 groups increases. And then we have a multi-ether series here where CF2O groups are the repeating units. In addition, there were some sulfonic acid ethers. Down here, these are all carboxylic acids. And these were associated with another production process at this fluorochemical plant. So these were all associated with the production of building blocks for fluoropolymers. This is called the vinyl ether process. And then these were associated with the production of Nafion polymer. So then in 2016, EPA issued a health advisory level for PFOA and PFOS at 70 nanograms per liter, like I showed before. And in that year, my postdoc May Sun and my master's student Elisa Arevalo and Mark and Andy and I, we published a paper in ES&T Letters that mentioned that there were very high levels of GenX and other fluoroethers in the actual drinking water in Wilmington, North Carolina. And so, this is highlighted here. The Wilmington drinking water plant has very advanced water treatment processes in place. They have raw and settled water ozonation, they have biofiltration, they have UV disinfection. It's really quite a state-of-the-art plant. But in terms of PFAS removal between the raw and the finished water, as you can see here, there was essentially no removal. This difference between raw and finished water is likely attributable to two things. One is uncertainty in the mass spectrometry measurements, and the other is that these two samples were, in essence, 24 hours apart because of the hydraulic residence time in the plant. So, but what was interesting is in 2013 to 2015, US EPA conducted the unregulated contaminant monitoring rule that included 6 PFASs. And when Wilmington submitted their samples to the lab, the only PFAS that was found among the 6 was this light green PFHPA. So based on the unregulated contaminant monitoring rule results, Wilmington thought they didn't really have a PFAS problem. The highest concentration they measured was 27 nanograms per liter. But then, we looked at a much longer list of PFASs and found hundreds of nanograms per liter of GenX in this water. And in addition, if you look at the red bar here, that red bar is repeated here. We found several other fluoroethers in this water at much, much higher concentrations. At the time, we could not quantify them because we lacked the analytical standards to calibrate the mass spectrometer. But it was clear that these compounds were present at very high levels. So, this paper was published in November of 2016, and, I've tried to get the attention of our state regulators on this issue, but really, essentially nothing happened until in June of 2017, an investigative report came out in the Wilmington Star News that highlighted the presence of high levels of PFASs in the Wilmington drinking water. And it was really this newspaper article that immediately caught then the attention of the community and public officials in the Wilmington area. And as a result of this public outcry, Chemours, the owner of this fluorochemical plant after, Chemours is a spin-off from DuPont, the city demanded that people from Chemours come to Wilmington and explain themselves. And within about a week or two, there was a meeting between officials from Chemours and public officials in Wilmington, and Chemours agreed to begin cessation of processed wastewater releases into their wastewater treatment plant, and from there into the Cape Fear River. So as a result of this reduction in wastewater releases, PFAS levels in the Cape Fear River dropped dramatically. Here from an estimated concentration of 40,000 nanograms per liter to several thousand to several hundred by October. So this was published by my student, Zach Hopkins, and back at this particular time, we still lacked analytical standards for a lot of these compounds. So we estimated them based on the mass spectrometry response for GenX. But we were curious, what the levels really were. In the meantime, we did get analytical standards for most of these compounds. And so my student, Shuhui Zhang, went back to an archived sample from 2015 to see what the PFAS levels were. And so the carboxylic acids were at 120 nanograms per liter, the sulfonic acids at 45. So elevated, but not super high. But then the fluoroethers summed up to 130,000 nanograms per liter. So these are incredibly high PFAS levels by all standards. So this is the impact on a downstream community. Wilmington and Brunswick County are about 90 miles downstream from this fluorochemical plant. If you look here at the other route of emission, it's the air emissions, and so air emissions lead to then dry and wet deposition of PFASs, and that then can lead to contamination of groundwater in the vicinity of these manufacturing sites. So our Department of Environmental Quality began looking into this, and so I always like to say it literally rained GenX in North Carolina, and here is an example of GenX concentrations in rainwater. You can see levels up to 800 plus nanograms per liter. And so this is the way the groundwater in this region got contaminated. And as a result of this knowledge, then there's been a very large effort to understand private well contamination. Between August of 2017 and December of 2020, over 5,000 private wells have been tested, and PFASs have been detected more than 10 miles away from the plant. So, this is a rural community, and people really had no idea that their well water quality was impacted by this manufacturing site. So the public has many questions. One is, are PFASs in my drinking water, and are there PFASs that standard methods are not picking up? Are PFASs in me, and at what levels, and what are the health effects? Are PFASs in the food we eat, and how can I get PFAS out of my drinking water? So a lot of these questions are really the motivation for our activities these days, whether it's through the Superfund Research Program Center or the North Carolina PFAS Testing Network. And so let me just briefly introduce this idea for the North Carolina PFAS Testing Network. So the North Carolina State Legislature basically declared that universities are more fit to uncover contamination associated with unregulated contaminants than the Department of Environmental Quality. And as a result, they charged universities in North Carolina with research to conduct research associated with PFAS occurrence in drinking water sources, among other things. So as a result of this, my lab and my colleagues' lab, Lee Ferguson at Duke University, are sharing this task of analyzing every municipal and county drinking water source in the state of North Carolina for PFASs. And we're doing this work in collaboration with Mei Sun at UNC Charlotte. She's working on the adsorbable organic fluorine analysis. So this is a surrogate measure for total PFAS, if you will. And then we're conducting at Duke and NC State targeted analysis for 48 PFASs, and also untargeted analysis using high resolution mass spectrometry to see whether there are any PFASs in addition to the ones that we're targeting. And so, part of the challenge was how to collect all these samples. So we worked on the traveling salesman problem, and in our Center for Geospatial Analytics, they optimized the sample collection trips for us around the state. In total, we collected 376 samples and so the first round of 376 samples has been completed. The second round is almost completed now. And this is what we find. So this figure here, each blue dot is representing a concentration of an individual PFAS in an individual sample. And if you look at the pie charts, the bigger the red area, the more frequently a particular PFAS is detected. So when we look at the traditionally studied perfluorocarboxylic acids and some of the perfluorosulfonic acids, these are indeed the ones that are most frequently detected in the drinking water sources. But we actually had only one drinking water source where PFOS levels exceeded EPA's health advisory level. In total, there were 2 sources where PFOS plus PFOA exceeded the 70 nanograms per liter. In addition, the fluoroethers were found just downstream and in the vicinity of the fluorochemical manufacturer, but these were found at higher levels than the traditionally studied carboxylic and sulfonic acids. But for GenX, we did not see any water that exceeded the North Carolina health goal. If we look at the sum concentration of PFAS in these drinking water sources, you can see that the vast majority is either not impacted or very little impacted. So there were 285 drinking water supplies in the state that had the sum of 48 PFAS less than 10 nanograms per liter, 71 were between 10 and 70, and 20 were above 70. And if we look at the 20 that were above 70, a lot of them have a large purple bar associated with them, which is the color we picked for the fluoroethers. And so this means that a lot of the most heavily impacted sites are downstream of this fluorochemical manufacturer. But there are exceptions. So for example, the town of Maysville here does not have any purple in their bar. So this is a signature that's associated with firefighting foam. And the positive outcome of this PFAS testing network activity is that within a month of us finding these high levels of PFAS in the Maysville drinking water, they were switched to an alternative drinking water supply that was essentially PFAS free. So to address the question, are PFAS in me? We've been working together with members of the Center for Human Healthy Environment. So Jane Hoppin is an epidemiologist, and we applied for funding for an R21 So this is a rapid response program, and looked at the GenX and fluoroether exposure in the Wilmington population. So Nadine Kotlartz is the postdoc working on this project. She came to us from the University of Michigan, and it's been great to work with her on this. What we found in 344 blood samples that we collected in Wilmington, North Carolina, is that 99% of these samples had elevated levels of Naphthalene byproduct 2. 98% had this PFO4DA, and 87% this PFO5 DODA. And so, what's apparent here is that the compounds that are longer, that have a higher molecular weight, are the ones that are most frequently detected in people. The PFO4DA concentrations in drinking water were substantially higher than those of the PFO5. So the other thing we were interested in was to look at the change in blood level concentrations for these fluoroethers now that the PFAS levels in the river have dropped dramatically. And so when we look at PFAS levels in 44 study participants that we collected 6 months apart, you can see that the fluoroether levels are dropping, suggesting quite clearly that the majority of exposure came from the drinking water. So the other thing that I want to finish up with here is, what are some of the impacts on the public water utilities, especially downstream of this fluorochemical manufacture. And so there are large infrastructure projects ongoing right now in Brunswick County. They're installing a reverse osmosis plant at a cost of which has now increased to over $100 million. And this will also translate into additional operating costs of about $3 million a year for this community. And in Wilmington, North Carolina, they're installing GAC absorbers, and the cost of that project is around $50 million. And again, about $3 million a year in additional operating costs. And other communities around the state are also impacted by PFASs. And so some have started feeding powdered activated carbon. Others had to temporarily stop using one of their plants until they also installed emergency powdered activated carbon treatment. And others are evaluating treatment options for PFASs. So that's at the public utility level. And then for the homeowners around the fluorochemical facility, those that are most highly impacted qualify for a whole house filtration system. And so these consist of 2 activated carbon filters in series, each containing 200 pounds of activated carbon. And even these carbon filters have potentially only a relatively limited service life before these PFASs break through. And this has created a lot of unhappiness in the private well community because, for one, these sheds need to be installed and they get locked up by the company that basically is charged to maintain this. So the homeowner has no access to this. And there's pressure drops here, and both flow and water pressure have been impacted, and that has led to problems. So that's the story that I wanted to share with you. I do want to also share just quickly that we just moved into a brand new building on our new Centennial campus, and So while it's been a heavy lift to move our whole lab, we now have an awesome lab in place. And so here are some of the impressions from the new lab. This is our sample preparation area. Here are a couple of our mass spectrometers, and here's a setup we use to conduct rapid small-scale column tests to evaluate PFAS removal by different sorbents. So please stop by for a visit. If you feel cold, it's about 80 degrees in North Carolina today and bright sunshine. So with that, thank you for listening, and I'm happy to answer questions.
Thank you, Professor Knappe. That was a fantastic talk, and I'm sure there are questions. We have time for a few, and I'll just mention that we will be running our rapid small scale column test tomorrow in process lab, and Wednesday and Thursday.
Super.
But not with PFAS, with chloroform. Questions for Professor Knappe? While we're waiting for others to think of questions, I don't know if this is more of a comment or a question, but you know, it's been incredible how many positive changes your work and that of others in North Carolina has brought about in terms of getting, you know, PFAS out of products and so forth, and certain chemicals out of production. But it seems to me like a lot of work is still having to be done on the forensics, trying to figure out what PFAS compounds are out there. And it seems like that process could be sped up, and you know, we could just deal with this environmental contamination much more rapidly if the companies that manufacture these compounds would simply work in partnership with environmental scientists to, you know, let them know what the structures are, what are we looking for, and so then we can begin to perhaps anticipate breakdown products. And I wonder if you have any comments on that, or if that is getting better.
Yeah, I think that's really a key challenge, and one of the challenges is the availability of that of analytical standards and the disclosure. So for example, when the consent order was issued by the EPA for DuPont to start manufacturing GenX, they redacted the information about the identity of these compounds. You know, they were called pre-manufacturing notice 109 and 110 or something like that. So it's truly a black box for everybody out there. And I do think this has to change, but you know, these manufacturers keep fighting this, and to Chemours' credit, they have shared analytical standards with us, but other PFAS manufacturers are fighting that very hard, and it's, you know, I think we're getting better at the forensics piece, but I think it's just a fundamental failure of our regulatory system that we can't get over this.
Yeah, it's incredible, really, all the work that's going into it. And again, it could be streamlined so much if
Right.
you had the information. So in the chat, we have two questions from two of our faculty here at Michigan Tech, and you can perhaps look at them, Detlef. But Noel Urban asked, are there standards for wildlife exposure? How do these compare with human exposure standards?
Yeah, so, and sometimes, so Michigan, for example, developed also wastewater effluent standards for PFASs, and they were based on the bioaccumulation of PFASs in fish, and then the, you know, also the food exposure route of contaminated fish to people. So the wastewater discharge standards are somewhat different as a result of those for drinking water standards. But I think it's still mostly a sort of a human-centric approach. You know, Minnesota, for example, has also fish advisories for PFASs, and so it's really in that context that these standards are being set. Here in North Carolina, we're working on a better understanding how bioaccumulation of PFASs occurs in the food web, and so we're starting with essentially with algae and all the way up to alligators to understand bioaccumulation of PFASs. But I don't know whether that will lead to different standards in the end.
Okay, thank you. And then Dr. Perlinger asked, what is the current understanding of how the PFAS compounds get into the atmosphere and the precipitation? If you want to take this shot.
When these fluorochemical building blocks are made for the fluoropolymers, byproducts are generated. These byproducts are often neutral compounds. They're called acyl fluorides. So instead of a COOH group, you have a COF group. And so these are essentially gases that are emitted up the stack. But the COF group hydrolyzes very rapidly to form the acids. So just with the humidity in the air. And so that is the pathway of emission and then the fate. And once you have the acid, then primarily through wet deposition, these get returned back to the ground.
Great. Professors Urban and Perlinger, if you have, there's a follow-up from Dr. Urban. So he asked, what is done with the spent activated carbon? Is this a problem, long or short term?
Yeah, so we're looking into this in the context of one of the most common management strategies for spent activated carbon, which is thermal reactivation. And so we're beginning to study the fate of PFASs in thermal processes. The PFAS, the vast majority of PFAS are likely mineralized in these thermal processes. So they form hydrogen fluoride, which then gets scrubbed out with calcium hydroxide so that you precipitate out calcium fluoride. But there are important questions about products of incomplete combustion. So, for example, thermal processes may produce things like tetrafluoromethane or hexafluoroethane that are potent greenhouse gases. And there are concerns about potential dimerization and formation of larger compounds from radicals that may be formed in these thermal processes. So yeah, it's something we're trying to understand. Is thermal reactivation viable, or would one have to adjust conditions to make it viable? And as part of our Superfund project, we're also trying to understand, desorption of PFAS from activated carbon, and landfilling is another option for spent activated carbon, and it's unclear to what extent and at what rate PFAS may desorb from spent activated carbon, enter the leachate. The leachate may go to the wastewater treatment plant, and then the PFAS end up partly in the biosolids and partly back in the river. So, this concern about PFAS cycling is a big one, and trying to break the cycle is an important goal. So finding destructive processes that are safe is really, where a lot of research efforts are being expended at this time.
Great. So we have perhaps one last question from Eric Seagren. You might know him. He writes, hey Detlef, great to see you. Interesting talk. A few years ago, Dave Hand and I had a senior design team working with Grand Rapids, the city of Grand Rapids, Michigan, and they were retrofitting their rapid sand filters by replacing the sand with activated carbon. It seemed to work. Have you seen any drinking water treatment plants do, employ a similar approach?
Mhm. Yeah, so that's the cheapest way to retrofit a plant with activated carbon to have some ability for absorptive removal of organic contaminants. The challenge is that the empty bed contact time of these filter absorbers is relatively short, often maybe just 5 minutes or sometimes less. And PFASs, especially the shorter chain PFAS, are not that well absorbed. So that means while the GAC will initially essentially achieve complete removal, very quickly these compounds start breaking through. So you may have much more frequent GAC replacement needs than with a system that has a longer empty bed contact time. And that's one of the things we're also trying to understand, what is a reasonable empty bed contact time. The plants around here are going for 20-minute empty bed contact time, and at normal operating conditions, not at peak operating conditions, they might even get close to 40 minutes of contact time. And that then reduces the frequency at which the carbon needs to be replaced. And that replacement is always a disruption for the plant.
Well, great. I think you answered all of our questions. This was really a fascinating talk and really connects with a lot of the things that we're doing and interested in here at Michigan Tech. So again, I really appreciate you presenting today. This was just great. I'm getting more comments in the chat. People really appreciated it, and really a treat. And I should have mentioned in my introduction really that you have been really one of the leaders here in this issue of PFAS in the environment. We tend to get on these bandwagons, and you were definitely one of the pioneers. So again, thanks for sharing all of this, and you may even hear from us again with some follow-up questions, but thanks everybody, and especially thank you to Professor Knappe.
Well, absolutely. It's been a pleasure, and it's good to see familiar names and at least one face. Everybody else's video is off, but that's great. So thanks so much for the opportunity, and hope we can chat again soon.
Great. All right, we'll see the rest of you for one more seminar next week. We'll be hearing from some of our current graduate students. So thanks everybody.
All right, see you all later. Bye.